Okay.
Well, welcome everyone. We thank you for coming and to this session on the technical track. So it's my pleasure to welcome Alex, who's going to talk to us about xenotrophic gastronomy. So, Alex, take it away.
Hi. So the talk is Xenotrophic Gastronomy, Fine Dining on Mars. So to start with, some quick introductions. So hi, I'm Alex Sharp. I was the team lead of the Korolev Crater SAR group at the City State Design Contest last year. And so as part of that, we did a whole lot of research on, amongst other things, how do you feed this colony? And we didn't really have time to properly present all of that research. So I've taken this particular segment and turned it into its own talk. So one sort of key point here is xenotrophs. It's a bit of a strange term. But at the end of the day, what a xenotroph is, it's a fairly broad sort of category, and it's strange eating things. In this case, it's microbes that eat things that you wouldn't ordinarily expect. So continuing on. So the outline of this talk is going to be in three phases. The first phase is on extracting resources from Mars. How do you do that effectively? The second is how do you use those resources to produce biomass? How do you grow things with those resources? And then part three is how do you convert that biomass into useful building materials or other materials such as food? So continuing on, impact slash problem. So impact, why is this an important problem? Like, why do you care about solving it? And on the problem side, why is it a complicated problem to solve? Like, why isn't there an easy solution? And this comes down to sort of a series of related trade-offs between your material constraints, i.e. what can you actually build and what are the material properties of these various things? Energy constraints, so how much power can you produce? And what is the type of power? So for example, do you get lots of heat? Do you get lots of electricity or whatnot? And the logistics slash economics constraints, because at the end of the day, you need to ship in all of these components from Earth. And that is, well, it's a logistical nightmare, especially if you're after anything large. So if you go and think about, for example, a farm in your mind, farms are huge. They run at atmospheric pressure, they let light in to allow plants to grow. And from a materials constraint sort of perspective, that is very difficult to do. From a logistical perspective, that is difficult to do. And so this talk is on essentially how do you find a reasonable middle ground to a solution to all of this. So first major material, we are carbon-based life forms, we need CO2. So obvious question. So Martian atmosphere is mostly CO2. You'd go through and say, well, what's the problem here? You go outside, you reach, like, you grab yourself a bucket of Martian atmosphere, you're all done. The issue is that Martian atmosphere is both cold and very, very low pressure. And so when you're trying to make tons upon tons upon tons of carbon, moving that from low pressure to high pressure is very difficult. And so to do that, what we chose was what's known as ionic liquid. So people generally run into ionic solids, so things like table salt, or they run into like solutions of ionic substances like salt dissolved in water. These are very special substances because they are molten salts, but they are molten not at thousands of degrees, but at room temperature. And because they're molten, they're easy to pump, they're easy to use, because they're doing it at low temperature, they're reasonably friendly. But because they're ionic, they can survive at Martian atmospheric pressure and do chemistry with the atmosphere, and they do that without boiling, which is really neat. And so there's a paper down there that you can look up if you're after more information. And so the idea is that you pump that ionic liquid over, it reacts with the atmosphere, carrying away the CO2 and the trace amount of water that's in there. And then as you heat that ionic liquid up again, it then, like, that reaction reverses and it provides high pressure CO2 for you, which is nice and easy. So continuing on, nitrogen. So so there are plenty of plants and the like that will go and fix nitrogen by themselves. The downside of that is that it's very sort of energy intensive for them to do that. And it's very much a rate limiter of growth. And so what you want is ammonia, or better yet, nitrate, because things can still use ammonia, but ammonia is toxic. Ammonia is also useful later on because you can use it as a store of hydrogen, because cryogenic hydrogen is a giant pain to use. But if you decompose your ammonia, you can get as much hydrogen as you need, nice and easily. And so again, we're doing room temperature electrolysis. And at a larger scale, there is the Haber process, but the Haber process is, again, fairly heavy to use, but it is more energy efficient. So it's a scale of colony sort of question as to which one you are looking for. So continuing on, water is extremely valuable, both in terms of pulling it from rocks or the atmosphere, as we saw previously, but also recycling it. So if you go through and picture things mixing with water in your mind, so you've got things that mix like oil, so they form two layers, or you've got things that mix like salt. So you mix them together, the salt just completely dissolves in. So what these guys did was they found a solvent that does both, and it does both defined by the temperature. So what you end up with is a little sort of thermal loop where you pump it on one side, it absorbs all the water in out of your wastewater. You pump it to the other side, you change the temperature, and it splits into two phases, and you can pull the water phase just straight off. And so that's useful both because it doesn't require membrane like reverse osmosis. It doesn't require high pressure like, again, reverse osmosis with all that energy cost. And you can run this all off waste heat. So continuing on, you have DRI. Because if you go through and you look at what plants and animals are made of, you're not all carbon and nitrogen. You've got, phosphorus and sulfur and all of these other sorts of things. So DRI stands for the direct reduction of iron. It's direct in that you're taking crushed up rock that contains iron or other useful minerals, and you are hitting it with very hot hydrogen gas, in this case heated from a kilopower nuclear reactor. And so that is both extracting the water of crystallization. So that's water that gets trapped inside the crystal structure of salts or minerals or what have you. So it's sitting there as water. But it's also converting, so for example, your iron oxides, it's converting those oxides into water. It's pulling out the sulfur, it's pulling out the phosphorus, which it then uses, which we can then use for nutrients to go and grow things with. But more specifically, you end up with essentially a water cycle here, where you're taking hot hydrogen, it's reacting, forming water, you're splitting that water, that then reforms the hydrogen. And we also have SMR/pyrolysis over on the side there. That's another very interesting sort of process where again, you have this energy trade-off. Sometimes you don't have the electricity to run your electrolyzer, in which case reacting methane with hot steam will produce the hydrogen that you need without needing electricity. And you can use a similar sort of process. So remember previously we had the problem of getting CO2 and that it's low pressure outside. Well, if you go and heat up carbonates, they will again heat up and produce high pressure CO2 that you can again use. So now that we've got all these resources, how do we put them to use? First stop, methanotrophs. So methanotrophs are one of the xenotrophs. So xenotrophs, strange eating things. Methanotrophs, that strange thing is methane or other small carbon molecules. So in this case, on the left here, you have something that is fairly standard to any major base, because if you're using a Starship or what have you, you need to be making your ton of methane a day if you want to fly out a ship every 6 months. Now, what you're doing is we're bolting on a commercially available technology here. So that strain mentioned on the right there has been used to convert excess natural gas from oil wells into animal food. It's been sold as actual food. It has been used. It does work. We have nutritional information on that. And so you can do that at a fairly low amount of energy. So as I mentioned, you need over a ton of methane a day to refuel your Starship. You need about 5 kilograms a day to go and feed a person. And so for a slightly larger scale colony, If you had a proper advanced reactor, you can convert 1 kilogram of uranium into 850,000 person days worth of food. And given the logistical choice between shipping 1 kilogram of uranium and 850,000 cheeseburgers, I know which one of these I would choose. And just as one last point here, so pyrolysis is a process of basically very high temperature, well-controlled burning. So you notice how we have biomass coming in here, so that's being recycled, it's being broken down into carbon monoxide and hydrogen. That ratio that it's producing is important, and they'll come up later. And the other side is trash. So you can go through and be making food out of your plastic trash that you've turned back into carbon monoxide, you've recycled, which I think is very interesting. And as a final point, because this is a microbe and it's growing in 3D, it's much more space efficient. So continuing on, the Formate Cycle. So this is an experiment. This isn't commercial technology. What they do is they engineered a metabolism to run off formate. So you can electrolytically create a whole bunch of formate by reducing carbon dioxide. And so you end up with this really interesting electric powered organism. And because it's E. coli, there's this massive data bank of things that you can use this for. And you've got the reference down the bottom there. So going back into more conventional farming, Cyanobacteria. So this was a successful experiment that was performed this year. And so it was growing cyanobacteria in a low pressure environment. And again, going back to those material constraints, by using a lower pressure, the stresses on the materials is much lower. So you have considerably more choice in what you want to do. Because again, you're growing something that requires sunlight, you need transparent materials, you want to make this on Mars, you're somewhat limited in choice here. And so the upside is that they demonstrated that it does grow, and it grows reasonably well. It will fix nitrogen, so it'll pull nitrogen from the atmosphere and use it to grow. It'll fix CO2, so it'll turn CO2 into oxygen, and it will grow, and it will extract minerals from rocks. So you don't actually need to extract those chemically. You can give it a bunch of gravel and it will go and grow off those, but it will do so more slowly. And on a somewhat related note, this was something new in our paper. So I'll have a link to the paper at the end here. So it's called ditch farming. And the idea is that rather than using, for example, a 3D printed frame to go and grow your cyanobacteria, you're growing it in water, and then you cover that water in an organic oil layer. And the weight of that oil layer presses down on the water, and so it increases its boiling point such that you can now sustain life. And so we chose oleic acid because it's easy to produce biologically, and it has some good chemical properties. If you look at the graph on the side there, anything past the red line, things will start to grow. Anything past the orange line, you've got a wide variety of things that you can grow. The primary issue with this is gas exchange. So as you would expect, you've covered this thing with oil, it's probably frozen at the top. Yes, it is transparent. Yes, it'll let light through. But once you've chewed through all of the carbon dioxide, nitrogen that's sitting in that water, well, all your cyanobacteria is going to starve. And so you need to be mechanically doing gas exchange, which may or may not be the best path forward. And that's sort of the point here. So continuing on, grasses. So obvious question, why would you grow grass when you could grow like tomatoes? Easy answer, growing tomatoes in an automated greenhouse is reasonably difficult. It is doable, but you need all sorts of robotics. Growing grass at scale requires a Roomba with a lawnmower attachment. Like, it's reasonably straightforward, and all of the supply chain of converting all of that grass into a whole bunch of glucose has already been done by the bioethanol people. So it's already been very heavily optimized. And in practice, when we're trying to grow large amounts of glucose for, again, bioethanol, we use grasses instead of normal crops because they are more efficient. And what's also important here is that these grasses grow at much lower pressure than people will generally tolerate. That makes the material supply, the material constraints a whole lot easier. But as the downside of, again, you need someone, well, you need a robot or what have you to go and collect it. And if you're doing that, mowing grass is much easier than other things. So putting all of this together, what you're left with is, so this is an aquaponics loop. So the idea is you're growing your plants, your microbes, that's producing a whole bunch of food. You feed that food to your fish. And again, the aquaculture industry is fairly good at optimizing fish production. So the overall ratios are fairly good in terms of converting your fish food into edible fish. You're creating a whole bunch of insoluble waste, which you're then digesting using, for example, fungus or insects or what have you. So that is, again, producing its own style of food. And then you're recycling all of these nutrients back into the plants and back into the microbes so they can then grow again. So putting all of that together, what you're now left with is some very interesting processed food possibilities, because you can produce simple esters like, banana flavor or what have you. Those are nice and straightforward. There are simple biological flavoring agents like vanillin, which makes vanilla, or even things like linalool, which is kind of essence of Fruit Loops. So you can take all of that, you can mass produce oils and fats. There are existing processes either patented for commercial use or in research use for making artificial milk, cheese, eggs, and gluten for things like artificial breads. So in terms of insects, people generally have issues. Well, in some cultures, people have issues eating insects, but people already eat insects in processed foods. There is a red food dye that is basically crushed up processed bugs, and people are fine with that. And similarly, you have mushrooms. And so the idea is that you can take all of these things to create a new palette that, even if you, for example, can't feed everybody with fish, making a fish burger or whatnot, which still contains some fish but is made of all of these other things, would then allow you to feed considerably more people in a much easier sort of path, because you've got all of these other things to use. So continuing on, synthetic meat. So synthetic meat ends up in the news from time to time. It is a very interesting solution to some of these problems here. The issue with synthetic meat is, well, has always been the growth media. It used to be that the growth media was a biological product, so trying to grow synthetic meat on Mars didn't make any sense because it required cows that you didn't have on Mars. That has changed. Now most of the growth media can be made out of fairly simple sort of organic materials that you can make using those GM organisms I mentioned previously. There are still some complex enzymes and the like that you need to import from Earth, but if you need micrograms or milligrams of those per kilogram of steak, that's still reasonable. This is also a subject of fairly active growth. So people are actively trying to make those last set of sort of hormones and the like, and make those through GM means. And once they do that, then this will be a whole lot easier on Mars, and you wouldn't need anything from Earth at all.
10-minute warning.
Okay. So next stage, creating rocket fuel. So this is, once again, something that is useful. So as I mentioned previously, pyrolysis cracks these large biomass sort of substances into carbon monoxide and hydrogen. It does that at one ratio. You generally end up with not enough hydrogen, so you can crack your ammonia to replace that. Of all of this, the hardest thing to make and store is your oxygen, and it is possible to, for example, store perchlorates, but there isn't a particularly good answer there. So going from rocket fuel to concrete, Biolith is a very, it's an interesting class of materials. So it is an artificial concrete where you have your waste rock coming in, and that's coated with various forms of biopolymers. And so by changing what polymers you use, what ratio you use, how you treat it after it's mixed, you can end up with a wide variety of differing things. And this has the advantage of, one, unlike a standard sort of bioplastic, you don't need to create all of the plastic there. You're only creating enough to, for example, to coat the particles of the waste rock. but you can still use it to 3D print things. You can still use it to cast out bricks and that sort of thing. And so for using it to create structures, so for example, the ditch farms that I mentioned previously, creating those walls out of this biolith is, again, very interesting. And so as a, so this is somewhat of a busy slide. And this actually ends up being a fairly large table in the actual entry. So if you're interested in this or any of the previous sort of information, please look up the paper. It's published both as a book and there is a PDF version on GitHub. And you can go and see more of the specifics as to how these things run. So if you look on the left there, I've noticed it's pyrolysis plus catalysts. So pyrolysis isn't really one process. It's essentially you're heating up this biomass, possibly adding water, possibly adding hydrogen, and you're decomposing it in different ways. And so if you look back into, for example, the beginning, you're decomposing it in very particular ways to produce your carbon monoxide, your hydrogen, so you can turn that back into methane or methanol. So your which is in and of itself useful, but sometimes you don't really want that. Sometimes you want more complicated things. So if you look at the top there, you've got the benzene derivatives. So that's useful as a solvent. It's very useful industrially. And much like it is reasonably difficult to ship over tons and tons of food, it's very difficult to ship over tons and tons of industrial chemicals to run even small scale production on Mars. And so being able to produce those locally using biological or semi-biological processes, that is very useful. And again, on the digestion side, you've got essentially GM bacteria producing things. There are already a suite of medicines that are produced using GM E. coli, for example, things like insulin, things like penicillin. You've also got the bioplastics, so PHB or PLA, which are well known and well understood for 3D printing, for example, high precision parts. You've got the oleic acid, which again can be produced, and that's one of the key ingredients of those ditch farms that we mentioned earlier. Aniline is also very widely used in things like plastics and the like. And on the left there, you've got ammonia, which in our case is very useful, both because ammonia is directly useful, like you can feed it to microbes and it'll use it as a nitrogen source, but also as a storable source of hydrogen, because cryogenic hydrogen, unlike things like cryogenic methane, you require very low temperatures, very specialized sort of containment. So storing it for long periods of time from a material science perspective makes very little sense. And so if instead you're storing ammonia, which will quite happily sit at basically Martian room temperature, then you can go and do that. And I think that is basically everything. Thank you very much. If you're after more information, please see the Korolev Crater entry from last year. There was a presentation that's up on YouTube with some more information, and there's also the book itself. Is there any questions?
Okay, you do have a question came in. Sounds
Yep.
like a bit like biomass can act as a kind of battery for storing the potential to meet a lot of different needs. What are the storage requirements for biomass? Does it generally need to be harvested and used within a particular time scale, or can it be quite flexible in that regard?
Okay, that's a good question. And it's also fairly interesting. So I'm just trying to find the... So part of this is that biomass is somewhat of a generic term. So, for example, if you're taking a whole lot of dried microbes or what have you, you can probably keep those out of the Martian surface, let them desiccate, and just sit there for as long as you need. If you're aiming to, for example, eat it, that then has some additional requirements. But also keep in mind that, for example, that methane, that methanol, all of that is in and of itself a similar form of biomass, in that as required, you can go and pyrolyze that and reuse it. And actually, while that question's there, So part of why methanol production is so important is because, unlike methane, methanol is liquid at Martian atmospheric temperature, and so it becomes very, very easy to store. And so if you need large amounts of carbon to go and do whatever it is you want to do later on, storing large amounts of methanol is much easier than storing it as, for example, plants, or storing it as, say, hydrogen or basic carbon. Yeah.
Okay, next question. I really love the Korolev Crater project. Very impressive work. Also really appreciate your crisp and easy to review diagrams today. No specific questions, but congratulations on great work. And I'll second that last part.
Thank you very much. Yeah,
All
it's
right.
been an awful lot of work, but it's been very interesting. The whole field is incredibly interesting. Yeah, thank you.
Well, we need to wrap this in another minute. If there's
Okay.
no more questions. Any more questions? All right. Well, let's wrap it. Thank you, Alex. It was a wonderful talk. Hope to see you here again next year.
Hopefully.
In person,
Thanks.
maybe.
Yeah, hopefully. Thanks.